thing I did, the main thing I did last time, I computed the green function of such free boson theory and at zero and at finite temperature. So first of all, as usual, I did the sort of Fourier transform, and it was a real Fourier transform with respect to space, with respect to x, with respect to space, and it was some discrete Fourier transform with respect to time, imaginary time, because here there is a restricted volume, and it is essentially integration is going on along the cylinder. So the cylinder is infinite in the x direction, and it is finite compactified in tau direction. And therefore, I have to introduce discrete frequency, and then it is just the sum of Gaussian modes, and then the average with respect to such functional is given by this expression, and then we can compute averages like this, and this green function was computed for zero temperature and for finite temperature, and for just a moment. Okay, and then for zero temperature, it was just logarithm of this thing with some constant, and for finite temperature, it was a bit more subtle, and what was necessary to do, it was necessary to make a summation, and here the exponential of I omega tau becomes 1 because I consider equal time correlation function. Difference in the tau is equal to 0. And then basically what one has to do, one has to make first this summation, and this summation is very well known, and it is, you can find it in all the table or do contour integral, and it differs from the zero temperature by this hyperbolic cotangent factor, and then what one has to do, then one has to do the integral over k of this result of summation times 1 minus cosine of k. 1 minus cosine of k because I had to subtract the divergency, and because of this there is not just cosine of ks, but 1 minus cosine of ks. And then you know how to do this integral. If you just write 1 minus cosine ks, mathematically will not be able to compute it, and the trick which for some reason is not included in mathematically is the following, that you differentiate this thing with respect to 1 over 2t, with respect to parameter. Then you do the integral, and then in the end you integrate over this parameter. So if you differentiate this thing with respect to 1 over 2t, this k cancels out, and then the integral becomes extremely trivial, and it gives you the result like this. So I have written how to do it, and this is for and then what you have to do, you have to integrate the result, as I said, integrate over parameter, because you first differentiate and then you have to come back, and this appears to be very simple, and the result is like this. Now, we see that if temperature goes to 0, this sign can be expanded, t cancels out, and you have the old result, a logarithm of minus logarithm of pi squared s squared. And okay, and then you what you should compare. So this is the green function at coincident times for the finite temperature and for 0 temperature as well. So now
Vladimir,
have to do, we have to remember.
Vladimir, if you could you maybe for me take a step back and briefly remind how did we go from the fermionic Hamiltonian to the gas of bosons, and where is now the beta for the boson?
I understand. I understand this question emerges. Many people ask. So you see, the thing is that there is the whole subject of bosonization of one-dimensional fermions. For that, there are very good books. For instance, there is a book of Alexei Zverik, Nersisyan, and Gogolin, where everything is written from A to Z. So you take the fermionic system, and then you show that you show essentially that this is how fermionic operator is expressed in terms of bosonic operator. So this is shown in more detail, in more rigor. So what I did, I simply gave you some intuitive, not a proof, but illustration of that, saying that if I put this factor to here, so what I will have, instead of K Fermi X, I will have K Fermi X plus this phase. Now, we know from condensed matter physics that if you have fermions, then the Fermi momentum is related with the density. So how it is related?
In 1D.
You should take the phase volume, which depends on Fermi momentum, and say that this phase volume is just this phase volume divided by 2 pi h to. So you do the, for instance, in 3-dimensional case, I show you in D-dimensional case how it is done. So it is simply because you are not not all of you are aware of condensed matter. So, how Fermi momentum is related with the density? It is related in the following way. So there is the Fermi surface, and this Fermi surface has a certain volume in the K space. So, if it is three-dimensional, then it is a volume, and the Fermi surface is sphere, then you have the volume of the sphere. If it is two-dimensional, then it is pi k squared, the surface. If it is one-dimensional, it is simply no, it is impossible. I mean, why not to throw it out of what is not functioning? If it is one-dimensional, then it is just the segment from minus K Fermi to K Fermi, and the volume of this is 2K Fermi. Now, the volume should be, so volume in the K should be divided by 2 pi h to dimensionality d. And this is the number of states which can be contained in this volume. And because this is the quantum cell in the phase space, and this is the volume of the phase space. So it is volume in the K part and volume in the real part. So that is the number of states which are inside of this volume. Now, for fermions, any state is populated exactly by one particle, and therefore rho is equal to this n divided by v, and so we will get a well-known formula that volume of the Fermi sphere divided by 2 pi h to the power d is the density. Now, in 1D, this volume is 2K Fermi, and d is equal to 1. So I always set units in which pi, in which h bar is 1. So then I have to divide by 2 pi in 1D. So there is K Fermi by pi, and this is the density. Now, if you have one-dimensional system, all what may happen is that the density may fluctuate, and this fluctuation is described by this term. So let us apply this formula when K Fermi slowly depends on the coordinates. And then what I will obtain that variation of K Fermi divided by pi is the variation of the density. Now, this is written here. And variation of the K Fermi is, the variation of the phase is K Fermi x plus or minus this phase. Then, if I differentiate the whole phase with respect to x, I have first Fermi momentum, the basic Fermi momentum, and then I have the derivative of this thing, which is interpreted as the variation of the Fermi momentum. And therefore, this derivative of phi divided by pi is the smooth part of variation of the density.
Okay, so
And
Vladimir.
this is written here. So then this variation in the density is the first term that appears is this variation because of the so-called sound mode.
Vladimir? So do I understand correctly that in higher dimensions we cannot do that because we don't have a linear dependence of the density of in the Fermi momentum?
No, in the beginning I'm in the Fermi system, right? And therefore the density, then it is a quantum fluctuation of the density.
Yes, but only in 1D. So in 2D or 3D we have like...
No, in 2D or 3D this only is not applicable at all.
Yeah, because we have
Not because of that, because of the following. This is this is strictly one-dimensional formula. But the trouble in high dimension is even worse, because in one dimension you cannot jump over the head of our particle. So all what you can do is just to make density fluctuations, because you may compress, you may depress locally, and this will be the density fluctuations. So, but if you are not in one dimension, but in two dimension, let's say, so you can go to the next chain and overcome. So it is, it is like moving in a narrow street where you cannot overcome. So if you move under the sign no overcoming, then you move with the velocity of the slowest vehicle. And if you have more than one lane, then you can overcome and situation is different. And here basically is the same story. So if you can jump over the heads of the particle, this means that you can create an excitation where one electron jumps and over, okay, and this is known as single particle excitation, right? Single particle, one particle jump and overcome the others. If it is strictly one-dimensional, such single particle excitations are not possible. And all what you have, this compression and depression of the density. And this is sound. And we know that sound is a boson. And that is why in 1D you can completely bosonize the situation. So you can equivalently have either fermionic description or bosonic description. If you are in 2D, let's say, then you have a mixture. You have sounds and you have single particle excitations. And then this bosonization no longer possible, because single particle excitations is Fermi. It is not boson in any sense.
Okay.
So again, this is some illustration, physical illustration. But if you want to go and study it in some mathematical terms, then there are good books, and I recommend very much the book by Alexei Zvelik, Alexander Nersesyan, and Gogolin. It is quite a bulky book, but it is written in some accessible terms. So and all the subtleties of this thing are explained. But I tried. I didn't want to give you a course of that. I just want to illustrate and use. And so it is not a derivation, it is an illustration. Now, then what is my goal? My goal is the following, that I have, let's say I have taken grids from the meta book of random matrix theory, where there is a chapter of mathematics which derives this thing. I did not want to repeat this chapter. Instead, what I wanted to do, I wanted to show that what comes out from this subtle mathematical derivation in the meta book, that it is in fact the result which can be obtained from free boson, from the free boson theory. Why it is so? Because we know that Wigner Dyson is equivalent to one-dimensional interacting fermions Kalozner-Sutherland model, right? Then the Kalozner-Sutherland model can be at large distances, at slow variations in the space and in the time. It can be mapped on so-called Latinger liquid. But the essence of the Latinger liquid, in fact, is that it is free bosons. So, therefore, if the analogy with Kalozner-Sutherland really works literally, then at the very least, all these results should be possible to obtain from free bosons. And this is what I have shown. I've taken the free boson action, and then I computed all the correlation functions, the density correlation functions, but in terms of this bosonic field. And then I have shown, so I did this calculus of free bosons. I have shown how to map fermions to bosons, but I did not prove that these bosons are free. This is proven in this book of, in many books, but in particular in this one. So the nice property is the following, that it is not only possible to describe fermions as bosons, it is more important that practically for every model, these bosons are free bosons. And free bosons, you know, it is the calculus which I did on this slide, so nothing is hidden. You can take your pen and compute all the correlations function. For free bosons, it is easy. The only thing that I did not show that after bosonization I have free bosons, but I sort of checked it because I went from the opposite side. I postulated that they are free bosons. Okay? And then I compute all the correlation functions. And then I see that these correlation functions are coinciding with what was obtained by orthogonal polynomial stuff. And we know that, on the other hand, there is an analogy with interacting fermions, and interacting fermions in 1D can be mapped on free bosons. So I did not derive that it is free bosons, but I checked that if I assume that it is free bosons, I get correct formula. This is what I wanted to do. And and basically how I checked it, I took this formula which was derived from by the method of orthogonal polynomials, and then I assumed that they can be obtained using the free bosons, and then what I obtained from these free bosons, that the correlation function like this, which appears when I substitute this thing into the expression for the density, then I obtain, in terms of bosons, I obtain that such combination is expressed in terms of this bosonic correlation function. And then this is one thing that I obtained. And the other thing which I obtained, that the non-oscillating part of this correlation function is given by the correlation function of derivatives, because each derivative is delta rho. And then I also computed this thing, and then I have to compare this expression, which is derived in a different way, with these two, which I derived from the free bosons. And now you see what happens, that that here there is the second derivative of the function g, and here too there is the second derivative of the function g. But then the coefficient in front, it depends on the ensemble. And on the other hand, the coefficient here depends on the constant in this free boson action. So in this free boson action, there is some constant. And now when I compare this non-oscillating part with this one, I see that k is 2 by beta, because if beta equal 2, then k equal to 1, and the coefficient should be 1 over 4 pi squared. It is correct. When beta is equal to 1, then k is equal to 2, and the coefficient is 2 by 4 pi, so 1 over 2 pi, indeed, correct. Then if I take beta equal 4, then this is 1/2, and then should be 1/8, and it is again correct. So by comparing this thing with the non-oscillating part of density correlations, I identify what is k in this free bosonic action. And now what is important is the following, that in general it is known that if you have some fermionic one-dimensional system and you do what is called bosonization, you always get the free boson similar to what I have shown to you. But where is the information about interaction? Because the fermionic model was interacting, and bosonic model is quadratic, it is non-interacting. So where is the interaction information? And this information is in this k, because it is known that if k is equal to 1, this means that the fermions that you used as an input there were three fermions. If k is greater than 1, for instance, for beta equal 1, this means that the fermions were attracting. And we know that if you look at Kravtsov-Sutherland, you will see by sign of the constant of interaction that indeed for beta equal 1 it is attraction. So okay, I will not find it, but believe me, you can find it yourself. Okay. And then if beta equal 4 symplectic ensemble, then k is smaller than 1, and this means repulsion. And indeed, Kravtsov-Sutherland for symplectic ensemble has a repulsive interaction. So we identified k. Okay, and now I have to check that the oscillating terms have correct amplitude. So you see that there is this factor e to g of s, e to 2g of s, and so on. And on the other hand, when I do the Bazinization, I obtain this correlation function, and I obtain, when I computed with 3 bosons, I get this identity. And so you see what this identity says, that the factor in the exponent, it depends first of all on k, but then it depends on the number of harmonics. So there could be first harmonic, second, and so on. And so let us, first of all, I told you in the beginning that the Fermi momentum for this problem is pi is if beta is 1 or 2, and it is pi over 2 if beta is 4. And this difference is because of the Kran's degeneracy in the symplectic ensemble. And then let us see. Let us first look at the unitary ensemble. So K Fermi is pi. If I look at this oscillating form and compare it with this one, I see that this n is equal to 1. Okay, if n is equal to 1, and for beta equal to k is also equal to 1, then this product is 1, and I have exponential of g of s. So here the coefficient is 1. Correct. So then I go to orthogonal ensemble. Now the same thing. So K Fermi is pi. Then here there is 2 pi n, and here is 2 pi. This means that n is equal to 1 again. N is equal to 1, but k now is equal to 2, and therefore 2 times 1 will be 2, and indeed the coefficient is 2. And then I go to symplectic ensemble. Here the Fermi momentum is this, and then I have 2 harmonics. So here I have only 1 harmonic, and here I have 2 harmonics, n equal 1 and n equal 2. So if I take n equal 1 and k 1/2, I should have 1/2 of g, and indeed I have 1/2 of g. And then I have second harmonic, then n is equal to 2, and k is equal to 1/2, and 1/2 times 4 will be 2. And again, and I see that indeed here there is 2. So basically what I can say that comparing what the formalism of free bosons give me and what comes from random matrix theory, from orthogonal polynomial stuff, for the unitary ensemble I derived it, for these two I did not, but this comes from the orthogonal polynomial stuff, and I see that all the relationship such as this coefficient, such as this coefficient here, all of them match the result of free boson of free bosons. And this is of course not a proof, but this is an illustration that the free bosons give you a correct result. So, but why I went to these free bosons? I went to these free bosons and somehow made you have hard time of thinking and understanding. This is for the same sake, for the following sake. If you have a free bosons, then it is very easy to introduce finite temperature. So you simply change this this limit of integration, and therefore I can obtain results for the finite temperature as well, and practically for nothing. And as I told you, what you have to do, you have to do the sum instead of the integral, and you have this result for the green function. So then you have to then you ask a question. Okay, I took the model of free bosons. I computed zero temperature, and it coincided with Wigner-Dyson. Now I can compute finite temperature from the same model, and I ask a question: what is, if any, the random matrix model that corresponds to finite temperature? And that was not, this is not trivial to answer this question, but luckily there is some method that can treat random matrices with no basis invariance, and in particular the power over the random matrices. And I will tell you now what is this method. So it is not the orthogonal polynomials. Orthogonal polynomials work only for basis invariant models. But if the models are not basis invariant, rotation of basis brings them to a different model, then forget about orthogonal polynomial, forget about all what is written in the book by Meta to the first glance. And it is the reason why mathematicians do not like, so they are very, very sophisticated in random matrix theory. They can compute very sophisticated correlation functions, but they can do very little if the basis rotation invariance is broken. But there is luckily some other method which, if I would have 5 lectures more, I would tell you what is it. but it allows to treat on the same footing. It allows to treat Wigner-Dyson theory and many of the theories that go beyond Wigner-Dyson. For instance, Pavlov and the Kravtsov. And so it is a method which you can think of it like the method which is used for non-invariant ensembles, and which is in that sense takes the place of orthogonal polynomial method. And this method is known as nonlinear sigma model, and it was invented by Kostya Yefetov in '83, and then for maybe 20 years or so it was used for different things, and all the results that we know about non-invariant random matrix models are basically from this method. So I have really no time to explain what is this method about. It is also a field theory, and moreover, it is a field theory which involves anti-commuting numbers like Grassmann numbers. So I could teach you that, but I need maybe 5 hours more. So what I want to say now is some remarkable formula which follows from this sigma model and which relates the energy level statistics with so-called classical spectral determinant. And classical spectral determinant is the following. Suppose you have diffusion. It could be maybe some not completely classical diffusion, but I use the word classical in the following sense, that if you have a system and if you have some formula that involves quantum interference of waves, then I say it is quantum, because interference is a quantum phenomenon. But if it doesn't involve interference, then I call it is classical, because indeed you may have classical system with long-range Hopf. The important thing is that different long-range Hopf do not interfere with each other. So if you have long-range Hopf, you do not have usual diffusion, because usual diffusion is only when you have short-range Hopf. And for long-range Hopf, you may have UV flights, which are much more efficient in propagation. But still, if you don't consider interference, it is still a classical phenomenon. And it appears, and I think it is maybe the best work of all in this application of the sigma model, is that there is a relation between the classical modes and the quantum level statistics. So first of all, let me tell you what I mean by classical modes. So let's start from usual diffusion. Take the usual diffusion equation. And then you see this is an equation which differs from Schrödinger equation only by the factor here, because in the Schrödinger equation there is I here, and in the diffusion there is 1. And this is important because if you have diffusion, you have a relaxation dynamics, exponential to minus something times t. If you have quantum mechanics, you have oscillation dynamics. And therefore, I told you last time about the revival phenomenon where first you put particle, it spreads first homogeneously after some time, and then it starts coming back to the point where it was injected. And this is a quantum phenomenon. And it would not be possible if there would be no factor I here in the quantum equation, because if there is a relaxation phenomenon, what is lost forever. Whereas if you have oscillations, it is not lost. It can, by interference, then revive. Okay, anyway, so now we are not about Schrödinger equation, we are about diffusion equation. So, of course, like in the Schrödinger equation, you can find eigenfunctions and eigenvalues. And for the usual diffusion, we immediately find that eigenfunctions are exponentials in time and in space, and eigenvalues are dk squared. Now, dk squared when you have an unrestricted volume. But if you have a finite volume which is restricted, then, as in quantum mechanics, your spectrum of eigenvalues become discrete. So you have now a set of eigenvalues. So if you have, let's say, some box and you insert the particle here, purely classical, what this particle does, it spreads, and eventually the probability to find at any point will be the same, because it is reflected from the boundaries, and there is an eigenfunction which is a constant. And if it is a constant, then the corresponding eigenvalue will be zero. So we always have a zero mode. If you have the restricted volume, then you always have a zero mode. And then you have non-zero modes. So in this box situation, if the size is L, then the epsilon n is simply d, and k is 2 pi by L, and then times n, if it is 1d. If it is more than 1d, then you have a quantization of kx, ky, kz in this way. But what is important, there is always n equal to 0. If n equal to 0, then your eigenfunction phi n is e to I kn times x, and if n equal to 0, then kn is also 0, and you have a constant eigenfunction. This means that there is a homogeneous spreading of the particle. This is important. So now, of course, if you know the eigenfunctions and eigenvalues, you can write then the probability in this way, and this is what we have in the usual diffusion. And this epsilon is, as I said, it is d 2 pi by L times n. So there is a zero mode, and there is a first mode. And the first mode is equal epsilon 1 is equal to d times 2 pi by L. No, there is, because I broke, so there is here k squared. Then here it is k, and in epsilon there is k squared because of this. And so the first mode is this. And then you see that this first mode, it is simply the time of the order of d by L squared, and this is the time to reach the boundary. So the first mode is the time needed to reach diffusively the boundary from the point where you created, and by orders of magnitude. And this is the physical meaning of the spectrum. And now and now we can generalize this thing for the case, let's say, of long-range hopping. So if there is a long-range hopping, then of course there is no differential equation, but still there is the same physics. You create a particle, and what it does, it spreads. It may spread faster than diffusion, but eventually, if there is no interference, it will be spread homogeneously. And this means that even if I have long-range hops, like in power low-banded matrix model, I still may write down something like diffusion equation, but instead of this differential operator, there is the integral operator. So there is this variance of the hopping, and then there is the average over volume of that. Why? Because I have to have a zero mode. So if I don't subtract this, I would not have a zero mode. But if I subtract this and say that I have a constant phi, then the integral, this integral gives me V bar times volume, and this is also V bar times volume, and I have zero. So this means I must subtract this part in order to have a zero mode, which physically is always there, because I have whatever is the propagation, eventually in classical limit, I have a homogeneous spread. So basically what I'm saying is that if you don't have interference effect, then you have classical propagation, which looks always like this. It is a relaxation dynamics, but this operator may be different. It could be differential, it could be integral when we have a long-range hope. But then, as I said, if you have diffusion case, then the eigenvalues are discrete like this, and then I can write down this is the eigenfunction, and this is the corresponding factor, which for the Schrödinger equation would be I epsilon t, but here is the relaxation dynamics, and there is minus. And what is interesting about that? The interesting thing is that if your time is greater than 1 over epsilon 1, and epsilon 1 it is a time of needed for particle to diffusively reach the boundary. So if if the time is much greater than this, and other quantum numbers are even larger than epsilon 1, then all the non-zero modes, n equal 1, 2, 3, and so on, all of them will be exponentially small. And the only mode which remains would be zero mode, because for zero mode epsilon is 0. And this is actually the condition. This is the condition where only zero mode is left, and this is actually the condition where whatever system you have, if time is bigger than that, you have the contribution only of zero mode, and this is the random matrix theory limit. So actually, even if you have a complicated and not really classical diffusion, you, I mean classical in the sense that it is the first mode is d over L squared. It could be a different system where the first mode will be differently depending on the parameter. But one thing is general. When the time is much bigger than this, then only zero mode remains, and this is the limit where random matrix theory starts to work for any system. So for any system, if you have large enough time, you should expect that random matrix theory will work. And this time 1 over E1 is known as a Taulis time. So if times are smaller than that, then random matrix theory doesn't work. All these correlation functions that we discussed will not work. But if you go to larger time or smaller frequencies, then you have the formula from random matrix theory, even though the system is not. Okay, so then let us do the following. Let us come to this situation where we have not a differential operator but the integral operator, and this is the variance of the Hawking. Now this applies for power low-banded random matrices. I think you have a particular power low-banded random matrices which is called critical when the variance of the Hawking behaves in this way. So it at large distances it is 1 over r minus r prime squared and not some other power. Then you can solve this problem. You can solve this problem of eigenvalues, and you find that the eigenvalues for the critical random matrix theory behave like this. So the dependence on n is here, and Kn is the same. It's the dependence on n is here, but if I send the system size L becomes very, very big, then this is small, I can expand, and then when I expand and L is cancelled, and I will obtain such zero mode, I mean, it is not, I obtain the eigenmode, but this is not an eigenmode, this is eigenmode normalized by mean level spacing. So, because the mean level spacing is inverse mean level spacing proportional to L, and this is the why this factor here appears. It is just normalization. And when I do this, and when I expand this factor because k is proportional to 1 over L, then L cancels out, and I obtain this thing. So you see, first of all, that why critical random matrix? Because if power here is different, then I would have a different power of n here. So this power of n equal to 1 is very special. Why? Because you have a one-dimensional system, and I mean the matrix. Each matrix can be viewed as a one-dimensional system with hopping, short range or long range, and in one-dimensional system, the power 1 is a critical one. Why? Because you know, like in two-dimensional system, usual diffusion with the power 2 is critical. We know that two-dimensional system is critical with respect to localization effect. So if you have dimensionality smaller than 2, then we have localization. And if we have dimensionality greater than 2, then we have phase transition, Anderson transition. And 2 is the critical dimension. Why it is critical? It is critical because the power of this eigenvalue is equal to the dimensionality of space. And here, such power appears only if there is second power here. It is very easy to understand because you see what I have to do. I have to do this integral, and if it is 1 over r squared, and then there is a phase volume which is r, then the result scales like 1 over r, and 1 over r is k, linear. Okay, so I found for the critical power law bandwidth matrices, I found the spectrum. And now comes very important, but unfortunately not fully accessible in terms of the derivation point. So there was already quite a while ago, possibly before you were born, that there was a paper by Andrei von Altschuler, and this paper, this result is basically philosophical. Why? Because what is on the right-hand side? On the right-hand side, there is the eigenvalue of classical propagation. It could be long-range Hopf, short-range Hopf, but no interference. It is a it is an eigenvalue of the classical propagation. And okay, so this gives you this determinant, and this stuff is basically the amplitude of it is an amplitude here, and this thing is just the derivative of the logarithm of this stuff. So basically, all the formulas for level statistics, they are expressed in terms of this e to g, or in terms of g. If I know E to G, I know level statistics, which is quantum, because level statistics is formed by interference. And on the right hand side, there is nothing quantum, there is only this classical spectrum of generalized diffusion, generalized spreading. So it is this formula why I'm saying it is philosophical, because it relates the classical stuff where no interference is present with the quantum stuff where interference is fully there. So to the best of my knowledge, nobody has a simple explanation how to get this. So there was, before this formula was derived, there were works by Rayleigh, and these are mathematicians who studied dynamical systems, so not statistical system like random matrices, but dynamical system. So you have dynamical system, and then somehow it becomes not unitary. So it is a big mystery how diffusion appears in dynamical system, because first you have a system which is unitary, where quantum mechanics, let's say, works, and you don't have relaxation. You have revival and things like that. But in the real world that we may observe and sense, we know that there's very little of revival. So if you die, you die. And this is essentially the world which is deeply relaxation. And diffusion is the simplest example of that. So, and the process how the unitary evolution, which is quantum mechanical, how it becomes relaxational, it is really a big problem, which because it is very simple to derive diffusion if you say, well, instead of dynamical evolution, I will consider ensemble of Hamiltonians of systems. So this is the great idea of statistical physics, to replace a very complicated problem of dynamics, to replace it by ensemble averaging. So it was the great idea, and it was a great progress of that. The whole thing that I'm talking about is ensemble average. But there is a deep problem how this comes that the dynamical system arranges itself in such a way that it becomes equivalent to ensemble average. And in this realm, people worked and continue to work so the idea is the following. The idea is that this happens because we, in general, it happens because we have an incomplete description of the system. So we cannot have infinite resolution. We have only finite resolution. And if we have a finite resolution, so your system becomes coarse-grained. And if you have a coarse graining, this means that it is an averaging over some cell. And when this averaging happens, of course, unitary dynamics is gone. In other words, you can say that in the environment there is plenty of ungapped modes, and all these modes work to destroy quantum mechanics. But again, what means destroy? Introduce a dephasing time. But the problem of dephasing time is basically of the same complexity as the problem of how unitary dynamics becomes relaxation. So that's why, you know, such type of the formula there were in the mathematical literature, in French mathematical literature, and the idea to derive something like this was coarse graining. So, because what is quantum dynamics? Quantum dynamics is such that if you have a chaotic system, so your trajectory folds, the problem is folding the trajectory, if it is a chaotic system. And this folding is very difficult to describe because it can return very close to the same point where it already was in the past. And somehow to simplify the situation, people say, well, we will introduce coarse graining. And then, once you introduce coarse graining, you immediately obtain relaxation of dynamics. And some formulas like this were derived by Rayleigh before. But it was, you know, since the complexity and the goal was much more ambitious because they dealt with dynamical system, and here we are dealing with ensemble averaging from the very beginning, so we ease our task. Then it was possible to derive the formula which is more, which is simpler, which is more transparent, and so on. So, okay, and what I'm going to do, I cannot derive this formula because for that we need sigma 1. It would be, you know, I bothered you by symmetry groups, then I bothered you by Latinger liquid. If I would start to bother you with the sigma model, so you will be okay. Anyway, so the physical meaning and this formula is really remarkable. There is some, I would say, mysterious relationship between the classical propagation and the quantum level statistics. So, but we can use it. So what I'm going to do, I'm going to, since we know this thing for critical power law bending matrices, so I can plug it here and see what happens. And here there is again a very interesting stuff. The point is that in 18th century, Euler, who at that time was, I don't know, maybe he was already in Russian Academy of Sciences, because his actually career was very interesting. So he was very young when, I mean, something like 23 years old, when the Russian Academy of Sciences was set up. And then they start to invite people from Europe. Of course, nobody wanted to go because thought that there are bears walking in the city, and it was not exactly like this, but still. But Euler, a very young German mathematician, he came and he spent some years, so he was very well paid, of course. So he spent some years there, and then he became famous. And the king of Germany, not Germany, it was Prussia at that time. And he said, well, what's going on? So our guy is serving Russian science, and we have to take him back. And he was paid, multiple times more. He came to Berlin, and he was working for 20 years or so, maybe 25 years there. And then the new Tsarist of Russia, Catherine I, who was actually German princess, she said, well, look, what's going on? I mean, there was a young talent. He was here in Russia. Then he was sort of transferred to Germany. We have to take him back. And she paid him multiple times more. And he came back. He came back and he was already 60 or something like this. And very soon he became blind. But this was absolutely exceptional man, because he returning to Russia, what he did, he mostly taught people. And he wrote a series of books, a big series of books that become actually the basis of all Russian mathematics. Russian mathematicians, the best of them, they all say that if not Euler, there would be nothing. And even though some of them were really very, very talented and self-made, like Kolmogorov, for instance, but he always said that I was made by Euler. One of the formulas in this book was this one. It is an infinite product, such like this, and it is equal to sine hyperbolic x by x. Now, if we take this spectrum linearly n for power law matrices and plug it, plug it into here, you will immediately see that you get an Euler product. And if you simply do very simple manipulation, so what you get that e to g, which is the factor in level statistics, that it is it's given by inverse sine squared. And then this is a remarkable thing. And now if you put it for instance here, so you will have the following. You can differentiate it, you can put it here, and these two terms, when g is 1 over sine hyperbolic logarithm of hyperbolic sine, then these two things become equal, and the total result would be similar to random matrix theory. In random matrix theory, we have 1 over 4 pi squared minus plus 1 over 4 pi squared s here cosine 2 pi s, and if I collect these two terms, you will find 1 sine pi s divided by 4 pi squared s s squared pi squared s squared. Now this is the square of the kernel of Wigner Dyson. Sine squared. This is the kernel of Wigner Dyson. So when I instead plug plug this as a e to g, then I will get the similar things. The only difference will be that you can do it. That instead of s squared, I will have this square of the hyperbolic sine, and some parameter t, which is expressed in terms of the variance of okay, so this is just coming from here, and so what I will get, I will get sine squared instead of s squared, but on the other hand, if I do 3 bosons at finite temperature, which is 1 by 4 beta b, then I will get e to g exactly of the same form. So, and it is also possible to check that for other ensembles you have the same thing. So this means the following, that the question which random matrix ensemble corresponds to finite temperature of Lagrange liquid or of 3 bosons, the answer is these are critical random matrix theory. The only thing is that this formula is possible to derive when temperature is much smaller than 1. So this means that this correspondence is not for arbitrary temperature, it is for small temperature. And yeah. And then, okay, 5 minutes. So, all what I did so far was just Lagrange liquid, and Lagrange liquid means that there is large distances, large times. And this means that this correspondence, which I just have been talking about, it is for small temperature or large B, 2 pi b, and large S. And here there is the correspondence of Latinger liquid at finite temperature and of critical aerodynamic sensor. But what about small b? Small s, so it is large s. What about small s? And it appears, so in 1994, together with Sasha Milin, we did the work which also follows from Sigma model, and we found the correction to density correlation function, which is okay, where S times this spectrum, which is pi st, which is smaller than 1. So it is temperature is small, and S should be not necessarily small with respect to 1, it should be small with respect to 1 over t. Okay. So there is this